Hey y'all, so in order for you to understand what's going on in rocket lab number 1, you have to have thought about Newton's laws and forces and how they apply to rockets and stuff. So that's what I want to do today, is just go through some of that stuff. Ooh, I just figured out how to do that animation. Alright, so let's talk about forces. And we've got a bottle that has most of the water in it, some of it that has half the water in it, and one that has no water in it. Let's talk about what's happening. So the air pressure that you create, which using the bicycle pump, is the force that changes the motion of the rocket. Okay, so remember, things are going to stay doing what they're doing until a force changes them. So the force pushing the water out causes the rocket to go up, to accelerate, to speed up, going away from the ground. However, once the water is gone, the upward force is also gone. So what does that mean? Well, that means the downward force of the weight, and weight is a force, and we often call it the force of gravity, which, for all intents and purposes, we'll say is the same thing. But so the downward force, the weight of the bottle, and the air friction immediately cause the rocket to start to slow down. All right. So, just way back when we talked about how gases behave. So we're going back and looking at that a little bit. Air pressure pushes in all directions, and you can see in that diagram above that it has arrows going in every direction. So the pressure is pushing everywhere. And if you think about this, gravity doesn't really play all that much of a role in getting the water out of the bottle. Because if you put, I don't know, fill bottle 3/4 full with water and then tip it upside down, it's going to glug, glug, glug the water out, and it takes a little while. Well, when you launch these, it takes less than a second. It takes about 1/3 of a second, in fact, for all the water to get out. So gravity really doesn't play a role in that. What happens is that the air pressure inside the bottle is higher than the pressure outside the bottle. All right, the little dots up there on the diagram, the red dots represent air particles. And you can see in the first diagram, they're all squished together. In the second diagram, they're much more spread out. The same number of particles taking up more volume results in the pressure going down. But anyway, so the pressure inside the bottle is higher than outside the bottle. Once the pressure inside and outside become the same, the water's no longer being forced out. So it's just going to glug out with gravity, all right? And the problem with that is, at this point, the upward acceleration stops because it's the pushing of the water out that pushes the rocket up. So what you really want is you want to get to the point where the pressure equalizes with the outside air at the same moment that all the water is gone. That is going to be your optimum amount of pressure and water to get you the most force. All right? So what happens if the pressure equalizes before all the water is out? Well, what happens is the weight, which is the downward force of the water that's left inside the bottle, will slow the rocket down very quickly, and you won't get the height that you want, or it won't stay in the air as long. If there's still a higher pressure in the bottle at the moment that all the water is gone, well, that's not as big of a problem. The deal is, though, that the force now has nothing to push on, and the energy is kind of wasted. It just goes out into the atmosphere as heat, and it could have been used to push the rocket higher. So it doesn't go as high as it could if there was a little bit more water in it. So that's where you're going, is you're trying to find that balance between equalizing the pressure and getting rid of the water. All right, so that's forces. So now we have to look at Newton's laws of motion. We've been through these, but now we're just applying them to the rockets. So, inertia, stuff's going to do what it does until a force changes it. So the rocket's sitting on the launch pad, it's not moving on the launch pad, it continues to not move until you pull the cord, and then the force created by the air and the bottle push the rocket up, right? So there's it, and you could use, there's examples of Newton's first law everywhere. On the way down, it's accelerating towards the ground, and then it stops when it hits the ground because the ground exerts a force on it. So there are lots of examples of Newton's first law in the launch of a rocket. Second law, F equals ma. So stuff accelerates in the direction of the force, and the greater the force, the greater the acceleration. So if you look at the two models, the red dots being the amount of air particles, there's a whole lot more air particles in the diagram on the right than on the left, implying that the one on the right has more pressure than the one on the left, which means the one on the right is going to accelerate more because it's going to have a higher force. All right, so rockets with a higher air pressure have more force. This all assumes the mass stays constant, so notice the two of them have the same amount of water and will accelerate faster. All right, third law. Forces exerted between two objects are equal in magnitude but opposite in direction. So, the force exerted on the water by the bottle air combo is equal to the force exerted on the bottle air by the water. Now, we're looking at two objects. We're calling the the bottle and the air one object, and we're talking about, and the water is the second. So the bottle and the air is one object, the water is the second object. All right, but the acceleration of the water is less because it has more mass. And whether this is intuitive to you or not, I don't know. But if you had 750 milliliters of water, your water then weighs 750 grams. The bottles, just bare bottles, I don't know what their mass is, but it's probably around 200 grams or something like that. So it's significantly less than the water. So anyway, this little table at the bottom is one way to look at Newton's third law when you're looking at the forces exerted between two objects. So the two objects we're talking about, the bottle and the air, is one, and the water is the other. The bottle and the air is pushing down, the water is pushing up. The forces exerted are the same, because that's what the law says. Forces exerted between two objects are equal in magnitude but opposite in direction. We just talked about the fact that the mass of the water is significantly more than the mass of the bottle. So that tells us that the bottle is going to accelerate at a much greater rate than that of the water because of the differences in mass. And that looks like it is it. Okay, so there it is for your last set of take-it-home notes for the year. And thanks. See you later.